Welcome back. Today in this lecture, lecture 29, we are going to study Bose-Einstein and Fermi-Dirac distributions. In fact, it's time now to go back to everything we've done and look at it critically from a quantum mechanical standpoint. We've spoken about quantum mechanics at different places in this course so far, but we have not really taken into account the statistics of quantum mechanics. And today in this lecture, we are going to consider quantum mechanical effect and how they affect the distribution that we have discussed so far. So when I talk about distribution, of course, it's probability of certain states that we have. So that's what we will do, and we will in particular introduce from a statistical standpoint the concept of fermion and boson, and we'll see that they have a profound effect on the statistics on how the particles can occupy a specific state in the gas of those particles. So before we get started, I'd like to spend a couple of minutes on some quantum mechanics, very basic. Of course, the expectations is that people who are taking this course probably already had a quantum physics course before. So just quickly in a couple of slides, so that things are clear for everybody. Basically, in quantum mechanics, we are dealing with quantum states, quantum vectors, sometimes we call them, and these are abstract objects that provide all the information of a quantum system. So, of course, we do not have access to that information until we have calculated or determined this state. But this is an object that can include all the information. Accessing it is a different thing. So it's a good idea because these objects are non-classical and therefore defeats the classical intuition to use a different notation for them, so that we make it clear at the outset that these systems are different from our classical intuition. And so that's for that reason I believe that the usage of the Dirac notation, like we have on here on the right hand side, where we have what's called a ket, is a good way to represent that abstract object. So of course the difficulty is to determine what that object is, and in principle it can be determined by solving the time-independent Schrödinger equation using the Hamiltonian operator H. Of course it's not easy to solve it, but there is a recipe, if you will, that if we can solve that problem here on the right hand side, we are able to find all the stationary state of the Hamiltonian and the corresponding energy. Now, what we often talk about is wave functions, and I think that wave functions are very useful, but can be somewhat misleading as not so much misleading, but the intuition about wave function is that it's just another function that we have to solve, and then we end up with a differential equation. And sometimes for students it's not as clear that you are really talking about a different type of object. But wave functions are being used a lot, and we will use them in this screencast a bit. And it turns out that the wave function is nothing else than a particular representation of the ket psi that we have here, the ket on the right on here. And so the way that the Dirac notation works is that you have a ket here, and you have a bra, and the dot product between those two objects is called a bracket, like here. And this bracket is a number that depends on x as a parameter, and this is what we call the wave function. So these are of course are the same reality. This is the same reality. It's just the preferred representation when you want to represent things in real space, in position space, like x. And in fact, the interpretation of that function is that the square modulus, because these are complex numbers, the square modulus times dx gives you the probability of finding a given particle between x and x plus dx. So this is the interpretation of this. Of course, the bracket itself, so the wave function, if you will, is a complex number. It's called the probability amplitude. This is not something that you can measure, but the theory relies on the probability amplitude, and that's what allows for interference and other effects in quantum mechanics that you do not see classically. So this is for the primer on quantum description. I think it suffices to say that we can describe a problem with a ket or a wave function. Now, we are in statistical mechanics. In statistical mechanics, we have a collection of objects, usually a lot of objects. So let's try to see how we build the collection of objects like this. And let's start with two objects, and that's what we're going to call exchange and symmetry. We are going to see that the symmetry of those wave function has, so the symmetry has a profound effect on the statistics. So this is essentially what we are going to do in this screencast, is to establish the relationship between symmetry upon exchange. So when we change one particle for another one, and what's its effect on statistical mechanics, and you will see that the effect is profound. So before we go there, let's try to have the smallest set, which is two particles. So let's imagine that we have two particles. One is positioned at R1 and the other one is positioned at R2. Of course, we know that quantum mechanically saying that is a little bit of a misleading, because you do not know where a particle is at R1 at R2, but let's say that the expectation value of the position is R1 and the expectation value of the second particle is R2. We can build a wave function now, which is called a two-body wave function, with two parameters R1 and R2, the first parameter being the position of the first particle, and the second parameter being the position of the second particle. I say this because if we change R1 for R2, the first parameter is still for the first particle, and so on and so forth. So the interpretation is just an extension of what I said on the previous slide, is that the modulo square of that function times dr1 dr2 is the joint probability of finding particle 1 at between R1 and R1 plus dr1, and particle 2 between R2 and R2 plus dr2. We have to use this probability and probability density because we have a continuous variable R1 and R2. Again, this is not necessary for this particular course here. This is quantum mechanics, and it's described in the other series of screencasts that I have on this channel on quantum mechanics, if you want to spend a few hours doing that. In any case, now what we want to do is to see what happens if those particles are the same. So if the particles are the same, let's say 2 electrons or 2 photons, they are the same. There is no way to say which one is which one. We know that the fact that we exchange them, so they are basically indistinguishable, so we exchange them, we expect that all the physics that we have will be the same. In other words, if I look at the energy operator, which is the Hamiltonian, if I replace one particle by the other one, I mean, if I exchange one for the other one, the solution, the energy spectrum, and the probabilities will remain the same. Mathematically, this is described as saying that the operator that exchange those two particles, which we call P12, and the Hamiltonian operator commute. It turns out this is important because, as you know, if two operators commute, we can choose the eigenfunctions of both operators to be the same. So in other words, another way to say the same thing is that the eigenstate of the Hamiltonian can be chosen to be symmetric under the operation P12. I'm going to say a few more minutes on this since it's so crucial. So now, because the two particles are the same, if I calculate the wave function, so the amplitude, the probability density of finding a particle 1 at R1 and particle 2 at R2, if I exchange them, of course, I'm not changing the physics. I'm not changing the probability distributions, since the particles are indistinguishable. So in other words, the square modulus before and after exchange of the two particles should be the same. This is basically translating the fact, this equality sign here, is translating the fact that the two particles are indistinguishable. So this has a profound effect, of course. As you remember, I mentioned a minute ago that the wave function are usually complex numbers. In fact, if you don't use complex numbers, quantum mechanics cannot be described this way. So what it means is that for two functions of which square modulus is the same, that means that the two functions are related by this equation here. Well, lambda is a complex number. It's basically a phase factor. When we say phase factor, it's basically a complex number that has a modulo of 1. In other words, it's a complex number that lives on the unit circle. Good. Now here's the thing. It turns out that because the system is invariant upon exchange of the particles, and because the Hamiltonian commutes with P12, there are only some values of lambda that are possible. And this is what I'm going to try to do now in the little box I'm opening on the right-hand side. So we call this operator P12 the exchange operator because it takes particle 1 moving into particle 2, and you see the definition is pretty clear here. The effect is to exchange the particle 1 and particle 2. So now particle 1 was at R1, now it's at R2, and particle 2 was at R2, and now it's at R1. Okay, now first thing that we can do is to, of course, write the same thing here, but I also learned that because the particles are indistinguishable, this wave function is equal to lambda times the previous wave function. That's what I established right here. Okay, very good. Now, usual trick in physics when we have something like this, we keep when we apply an operator to a function and then we get the same function times something. Well, what we do in that case, we reapply the operator again. If I reapply the operator P12 to the left-hand side of this here, it's equivalent to applying it here. Lambda being a number, it's not affected by the operator. So I do get that P12 psi R1 R2 is lambda psi R1 R2 according to this line. Therefore, we have this here. Now, of course, because we exchange particle 1 for particle 2 and then particle 2 for particle 1, we come back on our feet. Okay? In general, in 3 dimensions, we come back to where we started from. So basically, operating twice the exchange is doing nothing. But at the same time, it's also multiplying by lambda square, which is fine, right? Because we said lambda is a modulus of 1, so it's not going to change the probability, the modulus squared, so the probability density. Now, here's the thing. The way I've done this, it's lambda square. It is not modulo square of lambda. So the question is, what are the solutions lambda square equal to 1? Lambda being a complex number. Well, it turns out there are only 2 solutions. It's lambda is equal to plus or minus 1. And this fact, and you can prove this as I did here, just half a slide, that fact is crucial for the statistics. The fact is that the wave function, when we have 2 particles, for example, they must be either, they might have a lambda equal to plus 1 or minus 1. Let's see what it means just a bit more. So this is the result we had from the previous slide, right? So that when we exchange the 2 particles, the wave function changes sign or not. And again, this is not a problem for the probabilities since the probabilities are the square modulus. So we are fine with that. However, the wave function itself changes. It turns out, and then you can prove this pretty easily, I'm not going to do it here, but it turns out that every single wave function is either symmetric or anti-symmetric. You can't have a mixture of them. So that means that in physics, we have 2 types of particles. Particles that when you combine them, create a symmetric solution. So basically, symmetric means that when you exchange them, you get the same function. And we call them boson. This is the name of those particles. It's the same thing as saying that symmetric with a value of 1. And then we have the anti-symmetric, which is called fermion. And those are very, very strange indeed. If you do exchange one particle for the other one, you flip the sign of the function. And of course, I think that for students, the first time they see this, it's like an epiphany. Think about this. Imagine the 2 particles at the same place. Okay, let's imagine that the particles do not interact. There is no electrostatic potential or anything like that, but they try to be at the same place. Well, think about the fermion. Imagine that R1 is equal to R2. That would be the same place. But if the function at R1 is equal to minus the function R1, the only way for this to be true, of course, is the function to be 0. In other words, the square modulus at that position where both particles occupy the same positions, the square modulus of that function is equal to 0 as well. So in other words, the probability that the two particles will be at the same state in space is 0 because it's anti-symmetric. Okay? And so this is something that students learn usually, kind of almost a mystery. They're being told that the two fermions can't occupy the same position, but it's a direct consequence of this symmetry of the wave function. We do not have such a thing for the boson. Boson can occupy the same place. And these facts are going to impact the statistics a great deal, of course, because clearly we cannot have more than one fermion in a given state, and we can have more than one boson in a given state. So here we worked on the basis of the position space. As I said, this is a special representation of the ket in position space, but all this is true if you were using another label. Instead of using the position as the label, you could have used something else, like a spin, like a momentum, like anything like this could have the same consequence come. So let's try to see a little bit more here. Let's try to go back to our representation of the ket. It's very useful. And we are going to suppose that we have a particle that can have a state 0 and a state 1. If you want, it doesn't have to be, but if you want, you can think that let's say two particles that have spin, for example, 1/2 or 1. One is up and the other one is down, something like this. I mean, the two-state problem. So of course, if I have a particle in a state 0 and another state 1, I can write the wave function as a combined state like this, okay, a product of independent states. That's good. But this is one example. This is one particular realization. We could have the first particle in 0 and the second one in 1. There's one, but also the two particle in 0, the two particle in 1. I mean, in all generality, before we go into fermion and boson distinction. So in other words, if we are purely classical, and that would be, for example, in a memory chip on a computer, if we have distinguishable particle, we have all those four possibilities. First particle in 0, the second particle in 0, first particle in 1, second particle in 0, and so on and so forth. Now we already know that if the particles are distinguishable, and if we've discussed this when we introduced the partition functions, these two states here would be equivalent, right? If the two particles are indistinguishable, we just know one particle is in state 1, the other particle in state 0. So these two ket represent the same reality. So if they are indistinguishable and classical, it turns out that we only have these two things. I'm sorry, I'm using kets even for classical particles, but it's fine. We can use ket as representing a classical physics. We can describe the physics classically. That's what it means. But this is where things get easier, nicer. If we think about those four states, only some of them are quantum mechanically acceptable. Remember what I told you, quantum mechanically, all the states have to be either symmetric for boson or anti-symmetric for fermions. Sure enough, these two states, this 0, 0 and 1, 1, are symmetric states. So they are definitely acceptable quantum mechanically. But these two other states, 1, 0 and 0, 1, are not. They are neither symmetric nor anti-symmetric. But then this is where the linear algebra comes into the game, and we can do combinations so that we only have symmetric and anti-symmetric. So in particular, we can build 3 symmetric states from those 4. So 2 of them are trivial. These are the 2 states here. Of course, they are symmetric. Or a linear combination like this. And the plus sign simply ensures that if I replace 0 by 1 and 1 by 0, I obtain the same state. It's a symmetric state. The 1 over square root 2 is there for normalization. Let's not worry too much about this in this course, since it's not going to have too much impact in this particular lecture. Okay? Now, it turns out we can also create an antisymmetric state, and the antisymmetric state will be this one. It is, you can see the minus sign makes all the difference. It's antisymmetric, and I should say it's a very famous state. This state in particular, when you have spin 1/2 particle, it's actually the entangled state that we talk about in the different in basically in entanglement physics and quantum mechanics being entangled. This is usually the state that we look at. Okay, very nice. So we have all this. So this is very important slide here, because we really see that if we have two particles that can be in two states, we have 4 different scenarios. If we are quantum mechanic, if we are working with indistinguishable particles, we have those 3 scenarios, which is what those scenario is something very similar to what we've done with the Boltzmann distribution. This one is going to correspond to what we call the Bose-Einstein distribution, and this one will correspond to the Fermi-Dirac distribution. So this is what we are going to do in the rest of the screencast, is a direct consequence of this. So this is very important. I'd like to again tell you that, of course, based off this particular solution here, if it turns out the 2 state 1 and 0 were the same, right? It could be, I mean, that they are degenerate and they would be the same. No, not degenerate, they would be the same state. Degenerate would actually allow it. We would have, of course, 0. In other words, the probability that the two particles occupy the same state is 0, which is, again, the Pauli exclusion principle, but in this case, not applied in real space as I did in the previous slide, but applied in no particular representation using the case. Very good, we are making good progress here. So let's try to look at the statistics of identical particles now, quantum mechanically. So we had just 2 particles before. Now let's suppose that we have many identical particles, just like we do in thermodynamics, in the thermodynamics limit. So it turns out that we have actually developed the tools in a previous lecture using the grand partition function. And the grand partition function allowed us to have the number of particles being changing. So it's not a constant number of particles. And the chemical potential is imposed, so as just like also the temperature is also imposed. So it turns out that if we are going to use that particular grand partition function, and it's going to become clear to you why we do this. We could fix the number of particles at the end when everything is done, but you will see that for the formalism, using the grand partition function will make things very simple. So for the grand partition function, the grand partition function is described by this equation here that looks very much like what we did for the partition function, but with the additional term related to the number of particles that are in chemical potential mu. This is something we've done. And now we can build that partition function by summing over all the possible state of the system, including the different occupation of the state in the system, different number of particles in the system. It's also variable because it's a grand partition function. So let's try to study a little bit more how we're going to calculate this partition function for these systems of bosons and fermions. And this is what we are going to do for the rest of the screencast. So we are going to do baby steps. So the first baby step is that suppose that there is only one state available. Well, it turns out that the result we get for the just one state is going to be actually going to be valid for the general case. We are going to prove the general case as well, and then after that we will compare. So imagine that you have only one state available for particles. Okay, so the number, remember we are working with a grand partition function, so the number of particles can change and can be anything, including 0, which of course is not very useful in terms of the amount of energy involved. So the grand partition function in this case is going to be written this way. Why? Because the energy is the same. There is only one energy state, so clearly we cannot really, there is no sum over energies, but there is a sum over the number of particles that can occupy that energy. And of course, the fact that you have particles in the system add a terms beta mu to the system as well, mu being the chemical potential, which is of course the constraint that we use here. Very easy. So now fermions, well, we know fermions can only have, for the Pauli exclusion principle, as I just described at the beginning of the screencast, can only have either 0 or 1 particles. So if they have 0 particles, 1 or 0 particles, the sum is just a sum from 0 to 1. And of course, we obtain a result that's pretty straightforward, which is 1 plus the exponential right here. Now, as you know, most of the thermodynamic variables are going to be a derivative or a function of the logarithm of z. So that, why not calculate the logarithm right now? And the logarithm of z is going to be obtained trivially like this. Here, actually, I didn't do any calculation. It's just ln on the right-hand side. So let's put this result on the side for now. And let's look at boson for a second. For boson, all the occupations are possible. So basically, we can do a sum from 0 to infinity. So we can put as many particles on the system. And I'd like to insist one more time that here the number of particles is not fixed. We are working in a grand partition function. Okay. So when we do this, we remember the geometric series, and I actually added the equation here on the right-hand side for those who forgot. Well, you can apply this directly into this equation, and you obtain this result for z. So z here is correct for bosons. Now, of course, again, we can calculate the logarithm. And the logarithm, what's nice about them, of course, is that the logarithm of the fraction is minus the logarithm of the denominator. And then we find, and we're going to put that in the box as well, we find something that looks very much like fermions, with some minus signs that actually come, and are very important minus signs, as we shall see. So we can, what's nice about this is that even though fermions and bosons have vastly different behavior in terms of statistics, while the formula are similar. I mean, are different, but are similar. Therefore, we can condense all the results by writing it this way. And it's very clear when we do this that the plus sign is going to be for fermions and the minus sign is going to be for bosons. And we have this result here. So we are going to be able to carry that result to get other numbers and other quantities that we can look at experimentally. So first of all, suppose that we are still in the limiting case of just one state that's available. We can calculate the average number of particles on that state. And of course, if we have this grand partition function, we can calculate averages like we did before. And in fact, we calculate the average value n as being simply a weighted average, a weighted sum of the number of particles in each state divided by the partition function, the grand partition function. And here, this is the usual manipulation that we use with partition function and grand partition function. We end up with a derivative and then the derivative of the logarithm. And so we can use the logarithm of z that we had from the previous slide and calculate its derivative and get the average occupation number of that single state that we have. And then we get this result, the average occupation number for the single state, which we have the plus sign for fermions and the minus sign for bosons. Very good. So this is for a single state. It's, of course, a very much limiting case. Turns out, and I'm going to kind of a spoiler alert here, that result is going to be the same result, it turns out, for any number of states. But I'm not going to take that for granted. I'm going to prove it because I think there is some subtlety there that's important for students to be able to realize in order to understand a little bit what this statistics is all about. So let's have a look at the general case. So we are going to have a general case means that we have different states that we are going to label EI, and we are going to, so the cost of putting a particle in the I state is EI. And we also know that we are also defined the occupation number of that particular state as being Ni. So this is the number of particles in that state I. Very good. So the first thing that we want to do is to find a way to calculate the partition function for this, the grand partition function. And so we can consider, for example, one configuration of the system. And that one configuration of the system will be the first state being occupied by N1 particle, the second state occupied by N2 particle, and so on and so forth all the way. to infinity. So in other words, what we see here, and again, we can take advantage of the properties of the exponential, this particular configuration, okay, it's a specific configuration with fixed n1, n2, and so on, is going to be simply the product of all those exponential with ni coming here in the argument. Now, of course, this is only one specific configuration. We should consider all configuration with all possible value of n1, n2, and 3. So in other words, the grand partition function of it would be the sum of those products. So the sum here with this notation for the occupation means we sum over all possible occupations. So all, for example, if we have 3 states, we'll have and it's a fermion, we'll have 0, 0, 0, 0, 1, 0, 0, and so on and so forth. In other words, all the possible occupations of the state. Nice. We have this, that's good. So now it turns out, and this is the most important thing, this is the most important step, probably the hardest step of the entire screencast, is the one I'm going to do now, because Ni is actually independent on I. So let's try to explain. Suppose that you have a fermion. If you have a fermion, Ni is 0 and or 1, regardless of I. So there is no index I dependence on the occupation Ni. If you have a boson, same thing. Ni will be 0, 1, 2, 3, 4, 5, all the way to infinity. And it's also not going to depend on I. And because of this reason, it turns out that we can swap the sum for the product. And this is actually the result that we obtain. Now, personally, this explanation of the fact that because they are independent, we can swap them leaves me a little bit unsatisfied. So I'm going to spend one slide to try to give you a more reasonable, more convincing argument why these two equalities are the same. The reason why we do this is because it turns out that this equality here is going to be much easier to use than this one as we move forward. So let's try to do that. Let's show that this expression is equivalent to this expression. And we are going to do that for bosons first. So let's try to simplify a little bit the notation. And let's try to calculate here on the left-hand side and see if these two are equivalent. And we are going to look at the bosons. So because of this, we have a product of a sum of sums. So the sum is going to be the sum of all the occupations, so 0, 1, 2, and so on, of the state 1. So that's going to be, this first sum is going to be this one for I equal 1. Then there is going to be another sum for I equal 2, and so on and so forth. So all these sums are done over all the possible occupations, and because it's a boson, the occupations are 0, 1, 2, and so on and so forth for each of them. Now, we can actually explicitly develop this, and we are going to get a term like a 1, E minus epsilon 1, E minus 2 minus 2 epsilon 1, and so on and so forth, and we hold the sum. So what I invite you to do is to pause the screencast now and convince yourself of what terms you have here on the second line. It turns out that when you develop all this, we find that what you end up getting is a sum of exponential, and those exponential are simply the product, okay, the product of all the possible occupations that you have. So the sum here are each element in the sum correspond to a specific set of occupations. So for example, this one, there is two particles in state 1 and no other occupations. This one is 2 particles in state 2 and no other occupations. This one has 1 occupation of state 1 and one occupation of state 3 of nothing else, and so on and so forth. So in other words, it's the sum over all the possible occupations, and in each case we multiply, we do a product of all those exponential factors. So in other words, this term and these terms are the same. So this is kind of a proof by development, if you will. So I invite you to do it to convince yourself this is the case. Very good. So I like, again, and I said that a number of times, but I definitely need to insist on this. The number of particles, n, which of course, which is the sum of all the occupations, and the energy are not constant in this description. In this description, what is constant is the temperature and the chemical potential. So it's very important to know this, because if we did not have this constraint, we would have a very hard time to do these sums. Because imagine here, it turns out that in this examples, each of these exponential have two particles only. But clearly we have more than two particles. We have many more terms that have any particles, I would say. Let's try to look at the fermionic state case. It's actually the same difficulty as this one. There's nothing more. But I find that for pedagogical reason, it's always good for students, once they feel they understand this one, to go to fermionic state to cement their understanding. So I suggest that you first understand this before you try to understand the fermionic state, which turns out to be actually simpler, but just because it's more compact. For fermionic state, let's do this again. So left-hand side. So now, what's nice about the fermionic state is that we have fewer cases because the sum here of the possible occupations for state I is 0 and 1, right? It's a fermion. So in other words, each of these sums is just no occupation or one occupation. So it's like this, like this, like this. And again, we get the product coming from here of each of those possible combinations, which are, the combinations are just 0 or 1. We can develop this product, and when we develop this product, we obtain something that's very nice again. But we only have exponential where there is no, the prefactor in front of epsilon is either 0 or 1, right? 0 occupation or 1 occupation. And it turns out that if you pause again the screencast, you can try to put that on a piece of paper. You can convince yourself that this sum is simply the sum of all the possible occupations of those product of terms. So in other words, this one, there's no occupation whatsoever. This one just has one particle in state 1. This one is 0 particle in state 1, 1 in state 2, 1 in state 3, and 0 particle otherwise. So that's the idea. And so this is how you prove that this equality is true, or at least you convince yourself it is true. So of course, we do a sum of all possible products. And one more time, the note is the same as the previous slide, but I think it's important to remind you. Very good. So now we have a very important result. And this very important result is that the grand partition function is described by this formula here, which again, let's try to remember, it's a sum of all the possible occupations, depending if you have a fermion or a boson, and it's a product over all the states. All the states which are all single particle states. There are states where we put a single particle. So that's nice. What we see here is that the grand partition function is a product of the partition function of each state, basically, of each corresponding to each single particle state. So the degrees of freedom are basically decoupled and can be excited independently. That's very important because that means that we can actually look at what happens in the entire system, so in the collections of system, by focusing on individual state separately. So one more time, this is true because we fixed mu, but we did not fix the number of particles. I already repeated this a number of times, but this is fairly unusual for students to think that way. Usually students think about a constant number of particles, and this is what you usually do in the first years of physics education, which is fine, which is the way it's done. Okay, let's try to see about the consequence of this formula. That's the same formula as the previous slide. Let's have a look at the fermions. For fermions, this sum is just sum of two occupations, 0 or 1, so it's directly this. And of course, the logarithm again can be calculated this way. Why we wanted to swap the product and the sum is because the logarithm of a product is just the sum of the logarithm, which is of course very convenient. And then we can do the same for bosons. Here for boson, of course, the sum, it goes from 0 to infinity. And we have another geometric series which can be calculated also pretty straightforwardly. Again, I keep the product here. That's nice. And that means that the logarithm of this will be the sum of logarithm one more time like this. Now, it's easy to see to go from this line to this line by, again, promoting the denominator to the numerator, provided we put a minus sign here. This is very typical. And one more time, these two formula, one for fermions and one for bosons, are very much alike. They're just a different of signs. And then we can calculate, we can actually put it this way. We can write it in a condensed fashion. It's very similar to what we had for the single state, but here now we have a sum. So we do not learn much because it's already something we saw for the single state, but we learn a great deal in the sense that it's an exact result for the case of bosons and fermions for any number of states. So we can do the same thing and calculate the number of particles for each state. We can use the same formula as we showed a few slides ago for the single particle, that's fine. Or you can remember the grand potential. It's maybe a good idea to remember the grand potential, which is obtained this way, and giving the number of particles in the individual state using this formula. It might be a good idea to think about that. Now, that means that the number of particles here is simply obtained by the derivative of the logarithm. And when you do this math, which is fairly elementary, you obtain this here, which you can simplify by dividing by the exponential up and down, and you end up with the average occupation of the state I is given by this formula here, with a plus for fermion and a minus for bosons. So one thing that's very good, and this is pretty amazing, so it's a good idea to think about it, is that the occupation of state I only depends on the energy of state I, which is, you may wonder, this is a bit surprising because, well, surely the occupation of a state should depend on how well the other states are occupied. Not so, because remember that in this formalism, we do not work with a constant number of particles. If we worked with a constant number of particles, of course, the occupation, if occupation of a state is high, the other occupation of other states will be lower because there is a zero-sum game. But there's no zero-sum game here because the number of particles is not a constant in this formalism. Very nice. So that allows me to say that the occupation of each particular energy state can be obtained by this. Of course, since this is exactly what I obtain, because there is a one-to-one correspondence between the state I and its energy. So this gives me the next result, which is of course a crucial result in physics. In fact, it's a key result in physics that goes well beyond thermodynamics, is that we have the Fermi-Dirac distribution for fermions and the Bose-Einstein distribution for bosons. And it looks like the difference is very small. So if you didn't know any better, you would say plus or minus. Who really cares? Does it make any difference? It makes, of course, a huge difference. And we are going to look at that in the next 4 slides before we conclude this screencast. So we are going to look at this in a graphical way. I've decided to provide different graphs than the ones that are in the Blundell and Blundell books. There is nothing wrong with the graphs in the book. Is just to provide you a different perspective. The physics is the same. It's just for those to have multiple sources of learning material. So this is basically a plot I made here. It's very busy, so don't worry. I'm going to dissect it, where we have the Fermi-Dirac, Bose-Einstein, and Boltzmann distribution for different temperature. So before we go into this spaghetti mode, let's try to look at each distribution first. The Fermi-Dirac distribution is this distribution that corresponds to boson. And so here I plotted it for different temperature. So let's consider the colder temperature, so the blue curve. So the first thing that you have to say, because of the Pauli principle, the distribution is indeed, the maximum distribution is 1. So you cannot have more than 1 particle on average for each state. That makes sense. We know that from Pauli principle, but it's always a good thing to check this. When the energy is very high, the occupation is 0. This is basically, it's very difficult to excite those high energy states when there is very little temperature, when there is no thermal energy. And in fact, that occupation of high energy state goes down as the temperature goes down. So it all makes good sense. At actually 0 temperature, which I have not shown I'm not showing here, we have a staircase like. So basically at 0 temperature, there is no enough thermal energy to excite particles above 0. And this is all related to the fact that the exponential changes sign when you have, so not the exponential, the variable here in the exponential changes sign between mu, before and after mu. So this is an important result for the Fermi-Dirac distribution where we have all the features I just explained to you. Now let's have a look at Bose-Einstein. So the Bose-Einstein, just the only difference is there is a minus sign here. So this is what we have. And again, I plotted this for 3 different temperatures. So one thing that's very important to note right away is that the distribution, of course, never goes below 0. This is the number of particles. There is no negative number of particles. But this distribution is not bounded upward. It could reach any values here. And it makes sense because Bose-Einstein allow for multiple particles to be by the same state. Now, one thing that's very important to note is that this function is actually undefined below 0. And this is one thing that's very important. If E minus mu is negative, okay, if it's negative, this number, the occupation will be negative. So it's not physical. What I'm trying to say is that these functions never go to the left of mu of equal mu. So basically all this space here, the negative space, is unallowed. In other words, and this is an important result for the Bose-Einstein statistics, is that for a boson, the energy of the boson must be always larger. So the energy of a boson must always be larger than the chemical potential. So if you pick the chemical potential mu to be equal to 0, all the energies have to be positive. And this is pretty clear from this thing. So you see the consequence of this is very important because that means even though there is only a sign change, you will see a big difference between the Bose-Einstein and the Fermi-Dirac distribution. It's a good idea to go back to Boltzmann. The Boltzmann was this purely classical view of things. We can actually consider them as indistinguishable. And if you remember how we calculated this for the partition function, we divided by n factorial. And we said, well, this description will be correct to divide by n factorial so long as I have many, many more states than I have number of particles. In that case, most of the state will be singly occupied. If you remember, that's how we treated this. But the Boltzmann distribution, the Maxwell-Boltzmann distribution, is going to be provided by these equations here, which is simply the exponential. Okay, so we know that this should be good when we have the number of levels is much larger than the number of particles. We've seen this before. So now we can go back to the more spaghetti-like things and compare. And this is what we obtained. We obtained this, and we see clearly that things. If you compare the 3 different, let's just focus on the blue for now. It doesn't. All the others behave the same. Let's just forget that. Let's just focus on the 3 blue lines. One is for the Fermi-Dirac is the full curve, the dashed curve is for Bose-Einstein, and the dotted one is Boltzmann. First of all, and we are going to discuss this, there is a pretty good match at high enough energy, while there is a very bad match at low energy. So let's try to understand this a little bit better. And I'd like you to also keep in mind how we work on this, where we have a fixed chemical potential. And so we are going to study this in terms of chemical potential. Now, what's a small chemical potential? It's also something that's not always intuitive for students until they took a full thermodynamics course. But let's try to remember what it means. If we have a small chemical potential, that corresponds to a small density. Okay, first let's try to explain this. Imagine that you have 2 systems. One system has a high density and the other one has a low density, and you put them together. What's going to happen? Well, the density of the high density system is going to is going to let particle move to the low density system. Okay, this is the way it works. This is kind of going to equilibrium. But we have studied that problem. We have studied that problem by saying that particles go from a high chemical potential to a low chemical potential. What I'm trying to say is that a low density corresponds to a low chemical potential. Okay, and if you're not convinced yet about this important argument, you can also remember how we calculated the chemical potential for an ideal gas, and we see that indeed the chemical potential increase with as a logarithm of the density. So what matters is that if we have a low chemical potential, we have a very low density system. Low density means very few particles compared to available state, right? Um, nice. So very few particles with for the compared to the number of allowed states. As we calculated, the allowed state being, of course, proportional to the volume. So all this works well. Now that means a small chemical potential corresponds to large value of E minus mu. So in that particular case, when we have very small chemical potential, we have many more states than we have particles. And so fewer and fewer states are going to be doubly occupied, which means that uh, it means that the Bose-Einstein distribution, the Fermi-Dirac distribution, and the Boltzmann distribution in that case will be the same. Because remember, the Fermi-Dirac distribution and the Bose-Einstein distribution were introduced to deal with these occupation numbers that was changing between them. Now, the occupation numbers is actually, we have almost no doubly occupied system. Therefore, it makes sense that they would match at low chemical potential. So that's what's important. So in other words, in this case, if we have um, low chemical potential, that means low density, the system behaves essentially classically. Now let's try to have a look at the other end of the spectrum, which would be the high density, in other words, the high chemical potential, so here on the left-hand side. So what we see here is that the changes are very, very different. And we, we see that for the energy equal to the chemical potential, we have a divergence in the Bose-Einstein. Okay, so that means that, as I mentioned already a minute ago, all the energy have to be above the chemical potential for the Bose-Einstein. And when we have very high chemical potential, so very high density, we start to see the importance of the fact that we need to have single occupancy on the state that are available. And this is the reason why things change so much between the particles. Clearly, the Maxwell-Boltzmann distribution still remains pretty close to some extent. I mean, somewhat close to the Bose-Einstein, but definitely different from the Fermi-Dirac distribution. So this was the last slide of this screencast. Of course, we have one more slide as usual, which is a summary. We have basically done two things today. We've done some quantum mechanics, and then we've seen that there are two types of particles in quantum mechanics, at least the distinguishable particles. We have undistinguishable particles. We have the fermions, which have an anti-symmetric wave function, and we have the boson, which have a symmetric wave function. So that may look like pretty much not important, well, until we see that that changes the statistics, the statistical distribution of those particles profoundly. And in fact, that's how we got to the Fermi-Dirac distribution and the Bose-Einstein distribution, which have, of course, a very important consequences on basically everything that we know as being matter. So I hope this screencast was clear to you, and I will see you next time for our next lecture. Thank you.